In this video, we're going to discuss design optimization in RISA-3D. We have an example model here set up that is a structural steel model with brace frames in one direction and moment frames in the other. I've set up section sets for this model so that I have columns, brace beams, braces, moment beams, and infill beams predefined with section sets. I could have also used members for this, individual members, not section sets, and done the same example, but I chose to use section sets here to make it a little bit cleaner. So we're going to talk about design optimization here, and so we still need to start with a given shape in RISA-3D. So we're going to have some starter shape. We're not necessarily sure what we need our final shape to be, but we're going to kind of take a guess at it, and then we'll let the program do the design optimization. So we're going to now focus on the design list and the design rules, which are kind of the two key elements to the optimization. The design list for a given shape is just that, just a list of available shapes that could be used. So the program decides which of the shapes from this list are the most optimal and presents that as a choice. There are, however, ways to limit the elements that are chosen from that design list, and that comes from the design rule. So if we open up member design rules, we can see that we have the ability to limit the depth, the width, and the code check ratios. So for the typical design rule, I've set a minimum depth of 8 inches because I don't want any of my shapes to be, any of my optimized choices to be less than 8 inches in depth. I may have connection requirements where I need that space there, so I'm going to set that to that minimum of 8 inches. However, I've set up a separate design rule without that depth restriction for my braces because I may, right now I'm using an L3 by 3 by quarter, and I don't want to use that minimum depth for my brace design. So that's my minimum depth, max depth, and then max and min width are the same thing for width dimensions, if that's a requirement. And then lastly, we have the bending check and the shear check, which allow me to potentially put some breathing room into my design. If I were to put, say, a 0.9 value for the max bending check here, then the program would do its design optimization but choose a member that only gets me to 90% of my code check rather than 100%. So that's an option for me as well. So I can set up all of my design rules. When I'm finished there, I'll come in and choose them for my individual section sets. And so that's already been done here. So we'll take a look at the model just quickly. We'll see we do have some member area loads applied. We also have some earthquake loads in each direction. So we'll be taking those frames in flexure here. We also have rigid diaphragms defined. So we kind of have a complete model here with some trial sections. So I've set up 3 simple load combinations here. So I'm going to solve an envelope solution. So the first place I'm going to check out is my design results. So if I open up the design results, my code check is what I'm most, which is my most important item here. I can see that I do have some failing members. So I have anything over a 1.0 code check is a failure. Then I also have some bracing or some unbraced length issues here with L over R ratios. So some slenderness things that are also a problem that are showing up in this code check. So I'm now going to take a look at my suggested design spreadsheet. So this is where I want to go to take a look at my optimization options here. So we can see on the members tab, we have my individual section sets lined up here. If I were using just members and not section sets, I would have each individual member showing up in this list. And so then we can see the current shape selected that we selected, and then the suggested shape that the program is choosing for us. So the program is optimizing based on strength criteria. So there's no serviceability checks here, so keep that in mind. So for our column section set, we can see that there was some failing members, and so the program is actually suggesting a larger member to meet our strength criteria. So it's going up to a 14 by 90, and we have multiple members in this column section set, and so the program will also tell me which program controlled for that suggested shape. So we can see that the program may design up or scale up our shape sizes in certain instances, and if we're coming up with low code checks, it may actually size down our members. And so we can kind of get a quick summary here, and then the last column gives us the opportunity as to whether we actually want to use what the program suggested or not. So in most cases, you probably want to run with it. In this case, we're going to say that for our brace beam section set, we need this 16-inch depth. So we don't want to go down to a 14. We want to keep our W16 member, so we're going to uncheck that checkbox. So once we get this all set up and we're happy with the selections, we can go up in the upper left-hand corner and choose our replace option. This warning is essentially saying, hey, you are going to now replace your current shape with the suggested shape from this dialog, and it's actually going to replace those elements or those members in our model. So if we say OK here, the program will do that replacing, and then it reruns a envelope solution, and then it brings us back into this member suggested shapes dialog. So we can see our brace beam is still here because we decided not to optimize that. So that will still show up. We also see a couple other shapes that are still hanging around. Note that if the shape that we are currently using is already the optimal shape, then your section set or members will not show up in this list. So we can see here that after that first solution or that first replacement, we still have a couple of shapes here that could be further optimized. And so what's happening, the program is going through that first iteration, it replaces the shapes with the new shapes and resolves the model. Well, when we do that replacement, we're changing the stiffness of the model and changing the load distribution to the model. So that can produce some different results after that next solution. So what we're seeing here is essentially an iterative procedure. So we may have to run this a couple of times to actually get our optimum behavior here. So we can see that our column section set and our moment beam section set are actually allowing us to maybe swing the pendulum back a little bit to a smaller shape. So we could run that through to completion. I'm going to jump over to the design rule spreadsheet again, and we can take a look at our code checks. And we now see that there's no members in the model that have any failures at this point. So we could do that further optimization, but we have shown that what we did with round 1 is sufficient. So that's a look at our suggested design capability within RISA-3D.